is Group 5 CrossFire.
Good afternoon, everyone. So I'm going to share my screen and bring up the presentation. I already know I didn't share it with audio. Okay.
We're CrossFire.
Okay, did everyone hear that first couple words?
I'm Sarah Carlini.
I'm Richard Oak.
I'm Tyler Smith.
I'm Alex Nix. Doctor is Dr. Zoo.
We wanted to create a system that allows a lacrosse player to maximize their practice time, even when they work alone. Typically, when a player wants to practice by themselves, they end up only being able to work on one skill at a time. If they want to work on their stick handling skills, but they don't have anyone to pass to, an easy solution could be passing to themselves by throwing a ball at a wall or using a bounce back board. If they also wanted to work on their shooting accuracy on goal, they could go to a field and use a lacrosse goal with a net cover, but without another person to pass to, they lose the advantage of practicing in a game-like scenario. Lacrosse is a fast-paced sport, so urgency when passing and shooting on goal is important. If a player is alone and has to stop after every goal they score to pick up a ball out of the net again and again, it prevents from using their practice time efficiently. So, in order to combat these issues, we designed the CrossFire, which acts as a portable lacrosse ball collection and launching system housed within the confines of a goal. This system allows players to work on their shooting accuracy and to work on receiving passes while going to goal at a game-like speed. The basic system consists of 4 main parts: target screen, collection basin, a transport system, and a launcher that sends the ball back to the player. So, in order to design this system, we had to take into account some parameters, including regulation, ball, and goal size.
So in order to begin designing the system, we had to first outline the requirements that we wanted the system to fulfill. We wanted the system to act as a target for the player to be able to shoot at and practice their accuracy. We also wanted the system to collect the balls and transport them from the collection area to a launching mechanism to actually launch the balls back to the player. We wanted the system to be portable and housed within a cart, so it was easy for the player to transport it. We also wanted the system to fit within the size constraints of a lacrosse goal and launch a maximum range of 30 yards. We also wanted to be able to change the orientation and pitch angles of the launcher. So once we were able to outline the requirements of the system, we were able to fill in the specifics. So physically, we wanted the target screen to be made of a shock absorbing material. This material, we wanted to absorb the impact of the ball hitting it, so the ball would drop straight down into the collection basin. Collection basin would collect and funnel the balls into one concentrated area and eventually lead the balls to the transportation system. The transportation system, we utilized a Archimedes screw with guide rails to lift the ball up and eventually transport it to the launching mechanism. For the launching mechanism, we used 2 parallel extension springs with a quick release system, and also we wanted the cart to be portable to make it easy to transport the system to a lacrosse field. For the electronic interface, we wanted to utilize an Arduino microcontroller. In this case, we're using a Mega because it has more ports for inputs and outputs. Also, we're utilizing a push button, potentiometers, toggle switch, and LEDs. To power the whole system, we are using a 12-volt battery to maintain portability.
So this is the initial design from last semester. At this time, we were using a pneumatic system to launch the ball, and the barrel had no direction control. Since last semester, we decided to make a number of design changes. For the collection system, the general design remained the same, but we added a kickstand to help balance the weight of the basin. The screw for the transport system was bulky and was originally going to be made out of PVC and copper tubing. For the launch system, as I mentioned previously, it was originally designed to be pneumatic, but due to safety concerns that were presented to us, we decided to move in a new direction, that direction being spring propulsion. Additionally, we also looked into adding manual yaw and pitch angle adjustments. And this is our finalized design. The first step in the collection system is the target screen, which is made of a 2-inch thick multi-purpose foam. And the purpose of this part is to be able to absorb the energy from the ball's impact. The main change that we made for this design from last semester is that the screen is no longer retractable, but instead is fixed in place. After coming into contact with the target screen, the ball will then drop into the collection basin, which is a slanted part that serves the purpose of moving the balls to the transport system. This part is made of aluminum 6061T6 and features 3-inch tall walls to prevent the ball from falling out. The system includes a kickstand welded to the bottom as a way to balance the weight and support the basin.
From the collection basin, the ball moves to the transport system, which the first step is an Archimedes screw. The original design we had for the Archimedes screw was going to be of a PVC drive shaft and copper tubing, but that was too bulky of a design and we wanted to slim it down. So we decided to use steel instead, and it could be easily welded and attaches directly to the motor. On the other end of the drive shaft is a ball bearing that allows it to spin freely. In terms of the motor that we were going to use, we intended on using a stepper motor, but after testing, we noticed that the motor was slipping, both at high and low frequencies, so we determined that we needed higher torque, so we switched to a 12-volt geared DC motor. Along with the Archimedes screw, we decided to add a guide rail subassembly to help the ball move straight up to the top of the cart so that it can actually access the launching system barrel. To do this, we used steel dowels welded to another steel part we called the reception area, which houses the ball at the top of the cart and is connected to the launching system barrel by a flexible 3-inch diameter hose.
So once the ball goes through the transport system, it will lead into the launching system. Initially, the launching system was comprised of a pneumatic compressed air launching method. We did have some challenges with this method. There were some safety concerns, so we had to make a decision to pursue other options. So after careful consideration, we chose an alternative launching method, springs. So we chose to use springs because it is much easier to analyze, much easier to test, and also much safer compared to the pneumatic compressed air method. So after choosing the propulsion method, we also decided to customize the workout for the player. In order to do this, we implemented manual adjustments for the yaw and pitch angles so they could practice receiving passes at different areas on the field. Noticed from our testing that we got our best results for launch range when we had a quicker release. In order to implement this into our system, we decided on a slip gear concept. This is commonly used in Vex robotics, and it is a gear that you grind some of the teeth off. And in this case, we have that gear meshing with a rack gear cut into that plunger rod. And as that plunger rod extends backward, those teeth will mesh. And then when it extends all the way, the smooth surface of the gear will be against the smooth surface of the plunger rod. When that happens, the plunger rod will be able to move forward, and it will be able to use the force from the spring to propel the ball forward.
This figure here is our circuit diagram. The microcontroller we used for it was the Arduino Mega. Previously, we had to use 3 separate Arduino Unos for the different components. This battery pack here represents the 12-volt battery. This push button is to start the whole system. This is simply a power switch. These 2 LEDs over here are status indicating LEDs. These 2 potentiometers adjust the launch distance and the launch frequency. This LCD display displays the information from these 2 previous potentiometers. These 2 DC motors represent the motors that are used for the screw assembly and the launch mechanism. 2 figures down here were the control mechanisms. The Arduino on the left was for doing the interface as the potentiometers, and the servo motors, which were going to be used originally for adjusting the pitch and yaw system. This Arduino over here was for controlling the stepper motor, which was planned to be used for turning the screw assembly. There were many exposed wires, and it was not very well organized. And so the new system, which was designed here, has status indicating LEDs to show whether the system is idle or if it's currently running. These 2 potentiometers allow the user to adjust the firing frequency and firing distance. The LCD display is a 16:2, which allows the user to read the set values from the potentiometers. This component on the left side is the power switch. These ports over here are where the power supply and the USB cable are attached for programming the Arduino. And this is the start button for the system. Our team conducted several different tests to prove that our device was able to accomplish our set goals. We did a test for the spring launching mechanism, a test for the foam energy absorption, and we did another test for the stepper motor for the Archimedes screw to prove that it was able to lift a ball or not. Our team conducted a spring launch test. The figure on the left shows the assembly we created for testing. Mitch Adams provided a large spring that we put within the barrel, and we put the wooden block on top of the spring and threaded the rope. It compressed the spring, which when we released the rope would launch the ball. During one of our tests, the rope snapped, which launched the ball at the greatest distance, which allowed us to pursue a more instantaneous release. We also conducted a test for the foam material for the screen mechanism. This test was to prove two things: that the material was durable enough and to test what required tension would be needed for the foam mechanism. We observed that as the foam material was under greater tension, the ball would bounce off of it, and when the foam was relaxed, then the ball would drop straight down. Also conducted testing for the stepper motor to see if it was sufficient enough to provide the torque necessary to rotate the screw mechanism. The first motor driver we had was significantly overheating, so we had to switch to another stepper motor driver, the A4988. We found that the motor was insufficient in its torque capacity, so we had to look for motors that were able to provide a lot greater torque.
In order to approximate the size of the springs, we performed kinematic and projectile motion analysis. From that, we were able to determine a number of different variables, including the optimal angle for launch, which was 42.9 degrees, the initial velocity of 57.3 feet per second, and the calculated time of flight of 2.4 seconds, which matched our experimental value.
So after finding all the components and materials that were needed for the prototype, our total cost would be $449.37. There were $526.66 in materials that were either donated or bought out of pocket. Our total budget that we had from the university was $500, which left us with a remaining budget of $50.63. This is the work breakdown structure, which is composed of mechanical, electronics, testing, and management.
Some of the biggest challenges we faced when designing the CrossFire were changing our launch mechanism from a pneumatic powered to a spring powered system, designing a quick release mechanism to release the tension on the spring, determining correct sizes for the spring as well as the motors, and finally the global pandemic, which affected every team. This prevented us from finishing our physical build. In conclusion, we created a device which was able to help lacrosse players increase their efficiency while training. The design was fully completed and we tested small scale to prove conceptual parts of the mechanisms. We used engineering formulas and concepts to analyze and find correct sizes for the components. We used our best judgment to select materials that would withstand the environment which the CrossFire would be used in. And as part of our design intent, we also made sure to minimize our costs and make sure that the user was safe. We'd also like to acknowledge and thank everyone listed. This was our reference. Thank you. Any questions?
So does anyone have any questions?
This is my team. I cannot ask questions.
Yeah, yeah. That's why we picked you, Dr.
They
Zill.
told me you should ask all the questions beforehand, and you cannot ask questions. I'm threatened, you know.
Oh, part of the plan.
Yep, we knew.
All the other faculty members are sleeping.
I don't know. I've seen them all semester too.
No,
I'll
we
take
are
it.
not sleeping. And just,
We'll take that.
Dr. Gamara, you want to jump in?
I
well,
don't think so.
no, I don't think so. I mean, I didn't have any major question. Yeah,
Okay.
it's just the challenge with this semester is that, I mean, a lot of, project did not completely reach to fruition. And a lot of my questions are kind of related to the actual final test, which were not necessarily expected. So yeah, I think they did a good job in terms of, revising some of the issues. Still, there is some safety issues, I believe, because remember that there was one of the judges last semester had some concern about you're still using the compressed air, right? To pressurize.
No.
No, we
You use
switched
that.
from the compressed
Oh,
air
okay.
to a
Perfect.
spring loaded.
Okay.
Yeah.
Okay. All right. Okay. So that means that you're taking those kind of concerns into account. Sounds good.
Yep.
We did have some videos for the testing, but due to the time constraint, we had to cut them out because there was several clips that were easily over a couple minutes.
Okay. So if people don't have any questions, I think if you have some maybe spare time, 2-3 minutes, do you think they can play the video? Do you have them available at hand?
Does anyone have those videos up? I currently don't have those videos up.
Media folder.
Yeah, you still have a couple minutes left.
Okay. Yeah, I'm ready if you pull those up.
Okay.
So did you guys do any kind of animation of the spring in software?
We did not.
Okay.
No.
And
that was something we could do
how
going forward.
confident do you think that your gear mechanism is going to work? The gear,
Yeah, the slip gear.
Yeah.
We're pretty confident. I did a lot of research into how slip gears are used. They're used mostly in VEX robotics, and I have a friend in a VEX robotics club at a different university, and he was saying they would actually be better if they were used with metal gears as opposed to they use them with plastic gears. So
Okay.
I think that would be something that could be doable at least. Obviously, we weren't able to prove out the concept at all, which would have been a lot better. But
Okay.
This was our first test for the spring, just to prove that it was able to fire a lot more consistently than the pneumatic system. So this is just us briefly testing in the middle of the greenway to make sure it worked. But it was right after this trial that the rope actually snapped and was able to provide a greater distance. Because when Tyler manually releasing it, it was still causing like some friction, and it did hit the side of the barrel, and so it didn't launch it great. I'll find the other video then.
yeah, I don't think we have a video of when the rope snapped, but yeah, like Amrit was saying, that was like an instantaneous release, and that got us thinking about that's probably more of like an impulse force that we need. So that's what kind of got us down that rabbit hole.
And then here's the video for the motor testing. If I can share it real quick. Share screen. So this is the initial hub that we're going to use to connect to the actual screw, but there was no torque in that system. So if I slightly bumped it, then it would basically just start slipping. So this is why we chose to pursue the geared motor method. So that's this clip. And this was using the updated motor drivers because, as we mentioned previously, the other motor drivers were significantly overheating. So that's that clip, and then one more for the foam testing.
Yeah, the foam testing was interesting because we kind of held it at different like tensions. Some of them we had a little looser, some of them we had a little tighter, and we got some interesting results from that.
Yeah, that was it. We had several clips, but just as a concept. Okay.
Well done, team. Great job. Thank you.
Thank you.
Okay, I see clapping.